A warm welcome to all the viewers for the course Strength of Materials, AME 302. Myself Thiapal, Assistant Professor of Department of Mechanical Engineering, JIS College of Engineering, is going to give you a detailed lectures on theories of failure. So, probably this is the part 2 lecture for theories of failure, because in the introduction of the theories of failure, I have already mentioned you about why we are studying the theories of failure. Means what is the reason behind to know the theories of failure that is occurring in any sort of element or any sort of product that we are basically designing, because it is very essential for all of us to know that what is the impact load or what is the permissible load that can be withstood by certain design of that particular product. So, unless you are aware the mode of failure or the theories of failure, it will be difficult for a designer to design a product so that the rate of failure can decrease. So, today we are going to discuss about, in this particular lecture, as I have already told you, that we are going to discuss about the stress strain curve for ductile material for low carbon steel. Then we are going to discuss about the stress strain curve for ductile material. We are going to discuss about the stress strain curve for your brittle material, and we are also going to start a discussion regarding the stress strain curve for elastic plastic material also, because unless you are aware of the diagram of stress strain, you couldn't find that at which type or which amount of energy, that is the ultimate stress it can be withstood by that particular, or the ultimate load that can be withstood by that particular element of that particular product. So, before we proceed with the detailed lecture of this theories of failure, let us have a look at the contents. So, in my previous lecture I have already discussed about the types of mechanical failure and what are the causes of failure, and today in this particular lecture we are going to cover up the maximum principal stress theory as well as what are the yielding surface corresponding to maximum principal stress theory. And in the upcoming lecture we will be discussing about the maximum principal strain theory and about that maximum shear stress theory. And in the upcoming lecture we will be also discussing about the maximum principal strain theory, maximum shear stress theory, maximum strain energy theory and the distortion energy theory. So, basically these are the 5 theories you can see that will be discussed in my upcoming lecture of theories of failure. So, without further delay, let us move to the next slide. So, this is the slide that we are going to have a discussion on the stress strain diagram for ductile material. So, as I have already told, if the fracture is occurring and if the percentage of elongation is above 15%, then only you can tell that type of material has to be a ductile in nature, and ductile means you are implementing load by virtue of which it can be drawn in. I mean to say, what is that ductility? If I talk about the ductility, about the property, you are implementing load which can be drawn into wear, then it is ductility. And malleability, if I talk about, if it is drawn into some sort of sheet, then it is malleability property. So, in the previous lecture we are aware of what are the definition of strength, hardness, toughness, creep, and we have also talked about the resilience also. These all are the various properties of some sort of material, of various types of material too. So, in this particular slide you can see that stress strain diagram for ductile material for low carbon steel has been shown here. So, without any further delay, let us have a look. You have seen here that 2 type of range has been given. One is elastic range, another is plastic range. So, elastic range and plastic range I would like to discuss in a very short. That is, the elastic range is there where you are, if you are implementing some sort of load, then a deformation is obviously occurring in that particular body. But at the same time, if you remove the load, then the material will regain its original position. That means, within elastic range, if you provide any sort of load to that particular object, deformation is occurring, but the deformation is not the permanent one. That means, after implementing the load, and if you remove that particular load, it will obviously come to regain its original position. And if I talk about the plastic range, then I must say this is all about the stress strain diagram, because we need to know what is the plastic range. It is also known as the permanent zone also, because after implementing the load, it will deform, it will change the shape of that property. But if you remove that load from that particular material, then it will not come to its initial position. So the most important thing is that elastic range is when you are implementing some sort of load, and if you are removing it, then it will obviously regain its original position. But in case of plastic range, if you implement load, if you remove the load, it will not regain its original position. So from here you are aware that how basically elastic range and plastic range is basically helping us to know or to show that where the permanent deformation is occurring in the material when you are implementing some sort of load. Next is that if I talk about the Hooke's law, then I have also told that stress is proportional to strain within elastic limit. So that stress is proportional to strain, that is the what we say also modulus of elasticity, that is stress by strain. So if it is within the elastic limit, that means it is obeying the Hooke's law. So here also we are talking about the stress strain. So if I talk about the stress, then I must say load per unit area, and if I talk about the strain, that is change in length by its original length, or even you can tell the strain in diameter to its original diameter, that is also called strain. If I talk about change in volume by original volume, then we are talking about the volumetric strain. So these are the various types of strain, that is longitudinal strain, and one is the lateral strain we are talking, as well as we have discussed right now about the volumetric strain. So what this basically diagram that defines us about the low carbon steel. If I talk about the low carbon steel, that means the percentage of carbon is less in that particular steel, and you can see that stress that has been represented by sigma y, and here it has been strain. And what you can see is that if I consider from this particular center axis to certain limit, it is stress is proportional to strain. So this is point P, where you can say the stress is proportional to strain. And this y portion is what? It is your upper yield point. It has been told y is the yield point. So till P, stress is proportional to strain within your elastic limit. That's why you can see this is the dotted line, it has been shown, and this particular range has been known as your elastic range. This particular range has been known as your elastic range. Now if I talk about this yield point, here what happens, there is no increase in strain. There is no increase in stress, but strain is occurring. So after certain time, you see this upper yield point, here you can obtain the maximum yield stress, and then you are coming to the down portion, there you can see here it will be occurring the minimum yield strain, and ultimately it is getting a curve, and this is your ultimate load a material can withstand. So when the ultimate stress, basically this is your ultimate stress, there is the ultimate load it can withstand, then what it is happening, if this is your failure, so here in between there is a neck formation, this particular portion it is known as your neck formation, this particular point it is known as neck formation. Why this is neck formation? Because if I talk about, this will occur only for ductile material. Please keep in mind, neck formation will obviously occur for ductile material, because whenever you are implementing load, it will create a tearing in nature. Before tearing, a neck formation will occur, and this neck formation will further get break at your breaking point. So this is the failure if this is none other than your breaking point. So if you have a look for the stress strain diagram for ductile material, then you can see this is your stress which is represented along y axis, this is your strain that has been represented along your z axis, So this is your y axis and this is your x axis. This is your x axis. And here you can see that there is an elastic range is there and there is a plastic range, and plastic, this is your elastic range and this is your plastic range. So elastic range is, again I am repeating, if you remove the load within this particular range, it will regain its original position. But in case of plastic range, if you implement the load and if you remove the load, it will not come to its initial position. That's why it is also known as permanent deformation. Plastic range is also known as permanent deformation. So this is all about the content of your stress strain diagram for ductile material. Now let's move to the next slide. So just have a look. So far we were discussing about for low carbon steel, and if I talk about the stress strain diagram for low ductility material, then you see the figure is occurring is something different. To some extent you can see, to some extent from the coordinate point till y point you can see stress is proportional to strain. It is going linearly and 2% offset is been shown here. 2% offset has been shown here. So this is the dotted line, it has been shown here. This is dotted line is denoting for your true engineering stress strain diagram. And if you talk about this particular diagram, this is the engineering stress strain diagram. So true stress strain diagram, you can see 2% offset will be there from the original position and it will be going to some point, again it will be getting what? It is getting linearly. So this is your true, and U means your ultimate point, that is the maximum ultimate load. Here it is implemented to get the ultimate stress, and then after that the failure is occurring. So in case of ductile material, here also you can see that there is a neck formation is occurring. Before breaking, a neck formation will obviously occur since this is a ductile materials. Again I am repeating, it is a ductile material, that's why the same thing it will occur. Okay. So this is your what? This is your breaking point. F is your breaking point, and before breaking what happens? Neck formation is occurring here. So this is a stress strain diagram where you can see that 0.2% offset has been done, and this is true stress strain diagram and this is for engineering stress strain diagram. So here you can see particularly that upper yield point, lower yield point graph it has been not shown, and to certain limit we are having also elastic range also as well as plastic range also, where it has been determined to know the stress strain diagram for ductile material. So you can see this is also having there. Now if you look at this particular figure, that is stress strain diagram for a brittle material, then you can see that for brittle material stress basically increase linearly with strain till the fracture occurs. So here you can see this is the fracture that has been occurred here at the ultimate fracture, that is the breaking point, and again the same thing, stress has been considered at y axis and strain has been considered at x axis. So there you are not getting any sort of upper yield point, lower yield point, but obviously for brittle material you are getting a proportional limit to before this fracture occurred, that is the ultimate stress there, that is the breaking stress that is occurring here. You can get I mean to say that proportional limit where stress is proportional to strain within the elastic limit, and this will be probably the point which will be denoted somehow here. Then what will happen? It will get break in this particular portion. So this is the portion of stress strain diagram for brittle material, and you can see that stress is there, strain is there, and again an important factor for this stress strain diagram for brittle material, I would like to say that is stress is basically increasing linearly with respect to strain unless and until fracture occurs. For brittle material, you need to know that there is no upper yield point, there is no basically yield point itself. So, if there is no yield point, then there is no case of generating the upper yield point and lower yield point. So, upper yield point is that where the maximum yield stress you are obtaining, and lower yield point is that you are getting the minimum value for the yield stress strain you are getting there. So, these two things is not associated for brittle material, it is only applicable for your ductile material. Okay. After that, what you are getting, that is after the proportional limit, I mean to say it is directly getting to some fracture, ultimate fracture, because for brittle material when you are implementing the load, the fracture occurs, because fracture basically occurs for brittle material and your percentage of elongation is always less than 5%. So, if it is the percentage of elongation is less than 5%, then brittle fracture is already occurring in that particular material. So, how you are going to get that upper yield point and lower yield point? And the thing is that zone, if I talk about the elastic zone, then again for proportional limit it will be within the elastic zone, and then permanent zone is coming, but for here in this case the permanent zone is very negligible. I mean to say for very small amount it is there, because after proportional limit to little bit extent it is going and it is getting a fracture, it is getting breakage. So, this is what happening for stress strain diagram for your brittle material. Now, in the next slide we will be discussing about the stress strain diagram for an elastic perfectly plastic material. So, elastic is also there as well as it is a perfectly plastic material. So, elastic plastic material, the stress strain curve is seems to be something different. So, what you can see? So, if you consider this particular figure for x and y axis, from the origin or the coordinate point, to some extent it is getting stress is proportional to strain, because the stress is increasing linearly along with the strain, and after that what you are getting? You are getting a curve. That means upper yield point is to some extent it is getting, then it is getting again a constant stress. That means though you are increasing the strength, there is no increase in stress, and sigma y is represented by stress along y axis, and this is your strain. So, again I must say stress has been considered at y axis and strain has been considered at your x axis. So, in this particular figure what you will be able to see is that to some linearly it is getting stress is proportional to strain. That means the stress value is getting increased linearly with respect to strain. After certain time there is a little bit increase in stress, then after this the stress is constant, but there is an increase in strain. So, this is basically for stress strain diagram for elastic and plastic material, elastic and perfectly plastic material. Now, let us move to the next slide. So, finally, we have came across the various stress strain diagram for all the types of material. It is ductile material, it is low carbon steel with a low ductile material, for brittle material as well as for elastic and perfectly plastic material also. So, now today in this next slide we are going to discuss about maximum principal stress theory, which is also known as Rankine theory. So, if I talk about the maximum principal theory, stress theory, it is also known as Rankine theory. As I have already told you, it is also known as Rankine theory. And according to this, if you consider any one of the principal stresses which is be denoted by sigma 1 and it is your maximum principal stress, and there is another sigma 2 that has been considered as minimum principal stress, or sigma 3 which has been considered to be exceed the yield stress, then I must say that yielding would obviously occur. So, in two-dimensional loading situation for ductile material where tensile and compressive yield stress are nearly same magnitude they are holding. So, sigma 1 is your maximum principal stress, which is also equal to your maximum shear stress, that is sigma y. I mean to say sigma y is what? Your shear stress along y axis. And if I talk about the sigma 2, it is your minimum principal stress. The value is also considered to be plus minus sigma y, that is the shear stress along your y axis. So, using this particular principal maximum principal stress theory, a yield surface can be drawn as shown in the figure, as well as yielding occurs when the state of stress is at the boundary of the rectangle. So, if you consider for an example, that is the state of stress for a thin pressure vessels, then I must say the maximum principal stress is equal to twice the minimum principal stress. Or you can also tell that sigma 1 that has been considered to be as a maximum principal stress, and this maximum principal stress for thin walled pressure vessel is none other than your hoop stress or circumferential stress. And if I talk about sigma 2, that is your minimum principal stress, it is known as your axial stress, or it is also known as your longitudinal stress. So, as the pressure in the vessel goes on increases, the stress is basically followed by the dotted line. And suppose you consider a point A and the stress will be still within the elastic limit, but at B, whenever your maximum principal stress reaches your stress, although your minimum principal stress is still less than your value for your sigma, that is the stress at y axis, then there will be a yielding which will start at point B. So, this theory of yielding has a very poor agreement with experiment. However, still this theory has been very successful for brittle material, because you can see that for maximum principal stress theory, what basically occurs is your maximum principal stress is getting to the extent of your sigma y value, and in case of minimum principal stress, you can see the value of sigma 2 is still less than your sigma y value. So, yielding at that particular point already start beginning for that particular section. So, if you talk about the maximum principal stress theory, then I must say this theory is also known as your Rankine theory, and accordingly to it, a material in complex state or stress fail when the maximum principal stress in it reaches the value of stress within your elastic limit. And basically in two-dimensional general stress condition, the failure criteria which will be considered as sigma 1, that is the stress, maximum principal stress, that is none other than root over of your stress at x axis plus stress at y axis by your 2 plus root over of this stress at x axis minus stress of y axis by 2 whole square plus q square, that is represented by your sigma suffix e. So, sigma suffix e is none other than the stress at elastic limit in an uniaxial tension test, and sigma y, if you consider, that is your yielding stress. And the most important theory is that this theory basically holds or found to be a reasonable way to deal with brittle material. Okay. So here you can see that maximum principal stress, it is holding a good position for your brittle material than any other material. So if you look at this particular slide, it is going to describe you about the yield surface corresponding to maximum principal stress theory. So this is your positive sigma y, that is the stress at y axis. This is also stress, this is also stress, and this is also stress. So this is positive coordinate, this is your negative coordinate, and sigma 1 is your maximum principal stress. And you can see with the elongation of this stress, you can see from A it is getting elongated, means when you are increasing the pressure inside the pressure vessels, then to some extent till A it is going here, and at B extent what is happening, the stress is getting elongated in a linear form. That has been already stated here. That is, if you consider that sigma 1 as the maximum principal stress, then it will be twice of minimum principal stress for your pressure vessels, and this particular maximum principal stress is also known as circumferential stress, or which is also known as hoop stress. As well as if you talk about the sigma 2, this is none other than the minimum principal stress, it is also known as the axial stress. And if you consider a pressure vessels and you are increasing the stress, then you can see that it has been told that it is also the stress is getting increased by the dotted line. So you see this is getting increased, this particular thing is getting increased by your dotted line. You can see how this is getting increased. That has been already shown it in this particular figure. So that I was telling that if I consider a point suppose A, the stress are still within the elastic limit. But if I consider B, where the maximum principal stress reaches your sigma y, although sigma 2, it is still less than your sigma y. So if you look at this particular figure, this sigma 1, it is getting increased, but sigma 2, if you talk, it is still in sigma y. So that has been told that yield surface corresponding to the maximum principal stress has been shown here in this particular figure or in this particular content. And what I was telling in the thing is that basically this theory of yielding has a very poor agreement with the experiment, because if you go with the experiment pattern, then you can see this is not so much effective one. So in that particular case, it has been implemented for your brittle material. And the theory of maximum principal stress failure, it is very much essential, or it is successful for brittle material, because in ductile material this thing cannot occur, because you can see that stress is also getting increased to some extent, then upper yield point, lower yield point, all this thing is arising, then there is an ultimate stress is there, then you can get an egg formation is occurring, then you are getting the brittle point. So various material have got various theory of failure. So if I talk about the brittle material, then the most important thing is that maximum principal stress theory is very vital for this type of failure that is occurring for brittle material. So by the mode of maximum principal stress theory, a designer can calculate that at what point the breaking can occur or the failure can occur. Then it is comfortable for them also to design the particular product. So finally we came to the end of this particular lecture. So hope you have understood that in particular this lecture we have discussed about the various stress strain diagram for your ductile material, that is also for low carbon steel. We have also discussed about the stress strain diagram for simple ductile material, even for low ductile material, even we have discussed for the brittle material, and finally we have also discussed about your stress strain diagram for elastic and perfectly plastic material. Because unless you are aware of the stress strain diagram, you are unable to know that where the breaking is occurring, or where the neck formation is occurring. So breaking point or the ultimate fracture point, it is very essential for all of us to know before we study the theories of failure, because this theorem all is depending upon this particular load, that how much extent it is able to absorb that particular load. And then finally we have discussed the maximum principal stress theory, and from this theory it has been came to a conclusion, or we have come to a conclusion that this theory holds good for your ductile material. No, it holds good for your brittle material. So here I conclude my part 2 lecture for theories of failure, and please stay connected with me so that in upcoming part 3 lecture for theories of failure we will be discussing about some other theory that are associated with failures of material. And thank you viewers for watching the video. If you have liked the video, then please stay connected with me, subscribe the channel, and also like the video and comment. Thank you viewers for watching the video. Thank you very much.